Welcome to the Mechatronics Revolution Fundamentals and Core Concepts. In this lesson, we'll talk about bipolar junction transistors, or BJTs. The objectives of this lesson are to first describe the operating principle and the key specifications of bipolar junction transistors. We'll also design transistor switch circuits using BJTs for a typical circuit that switches on and off on a load such as an electric motor. Finally, we'll identify the purpose of a particular circuit called an open collector output, and we'll learn how open collector outputs are used to interface sensors with microcontrollers. A bipolar junction transistor, or a BJT, is a common semiconductor circuit element that's used typically as a solid-state switch. BJTs switch on and off a current path by activating a second base path. Now, BJTs have two inputs, a base and a collector, and an output, which is called an emitter. A BJT is a current-controlled device where the amount of current that flows into the base regulates the amount of current that flows between the collector and the emitter. A small base current will usually allow much larger current to flow from the collector to the emitter. There's three states that we typically care about with a BJT: the off state, linear, and saturation states, and those are determined by the voltages at the base, collector, and emitter. Finally, we really only usually use the off state and the saturation state when using BJTs within electrical circuits for mechatronics applications. The voltage at the emitter is typically lower than the voltage at the base by about 0.6 volts. And we must always have the voltage at the collector higher than the voltage at the emitter, and that ensures that our BJT is forward biased. We'll also define two terms: the voltage drop across between the base and the emitter as VBE, and the voltage drop from the collector to the emitter as VCE. In many mechatronic devices, we will be switching loads that require high current. And those loads could, for instance, be motors, LEDs, etc. We'll switch these motors on using logic-level devices such as microcontrollers. And microcontrollers can typically only sink or source very low current. So they're not going to be able to provide high enough currents to drive a motor or turn on an LED. But rather, they'll act as a switching element that will switch on and off a current path between a battery or a voltage source and the motor. And that's where transistor switch circuits come in. Transistor switch circuits are used to switch the current path on and off through these high current loads. Here's a typical transistor switch circuit that's shown at the bottom left of your screen. And you can see that we have several voltage inputs. We have VCC, which is our battery voltage or our power supply voltage, and that's going to be used to provide high current through our load. Our load here is denoted as RC. We also have a voltage input to the base, and that voltage input is going to be driven by our logic level device, for instance, our microcontroller. Let's talk about how to analyze this circuit. And before we go through some of the detailed equations, we should note that when Vin is high, that will mean that current flows into our base and essentially turns that transistor on, which allows a current IC to flow between the voltage source VCC and ground. So it allows current to pass from the collector to the emitter and turn on that load, for instance, our LED or our motor. When Vin is off, or essentially the logic low voltage, then that's going to turn off the current path from the collector to the emitter, and it's going to turn off our load as a result. Let's look at those three states we mentioned in detail. First, we have the off state. The off state occurs when the base emitter voltage is less than about 0.6 volts. In that case, there's no current that flows through the load. And V out, we take a measurement of the voltage drop between VCC and V out, we will see that there's no voltage drop through the load resistor because no current's flowing, so V out is equal to our supply voltage VCC. Now, as that base emitter voltage creeps up between 0.6 volts and 0.7 volts, and we have our collector emitter voltage greater than 0.2, that will put our BJT into what's called the linear state, and in that case, the current from the collector to the emitter, IC, is going to be equal to a constant beta times the base current, IB, and that beta value is typically on the order of about 100. So the amount of current we put in the base will regulate the amount of current that flows through our load. Finally, we have the saturation state, which is when the base emitter voltage is greater than 0.7. In that case, V out, the voltage measured downstream of the load, is going to be equal to VCE, and that's going to be 0.2. So that's going to allow quite a bit of current to flow through our load, and the amount of current that flows through the load can be determined given the value of V out and our supply voltage. Let's design a transistor switch circuit using a BJT to control the current flow IC through our load using our input voltage Vin. When Vin is 0, that places the BJT in an off state. So no current will flow through the collector, between the collector and the emitter, and thus IC is 0, so no current flows through our load. Now the question arises, what voltage Vin do we need to place this BJT in saturation? So to switch the transistor from off to saturation and allow current to flow through our load, what voltage Vin is required? And we should note that typically for mechatronics applications for these switching circuits, we usually want to operate either in the off state to turn our load off or the saturation state to turn our motor or our LED on, and we don't usually operate in the linear state. To solve this problem, we'll turn to Kirchhoff's laws. To start out with, we can analyze the loop at the bottom left and look at the voltage drops across that loop. So Vin is equal to the voltage drop across the resistor RB plus the voltage drop from the base to the emitter. Secondly, we can also use Kirchhoff's current law to look at the current flow into the BJT. So the current IC is equal to the voltage drop from the source voltage VCC and the collector emitter voltage VCE divided by our load resistance. Finally, we have one more equation we can apply, and that's a property of BJTs just before saturation, where we have that constant beta that relates our base current to our collector current. And that equation is written as the third equation here. So using these three equations, we can actually solve for the voltage input we need to place our BJT into saturation. So you'll notice that we have three equations and three unknowns. The knowns in this equation are beta, which can be obtained from the spec sheet for the BJT, our source voltage VCE, then our collector emitter voltage, and our base emitter voltage, which is 0.7. Just before saturation, it's 0.7 is the required base emitter voltage. And then we also know our load resistance and that resistance RB. So these are all of our knowns. We can then solve for our three unknowns that we have and obtain the value of Vin that we need to place the BJT in saturation and turn our load on. Let's look at an example where we actually apply some numbers to this switching circuit. So we'll use this particular make and model of the BJT transistor with the parameter values listed in this table. So our question is, what input voltage Vin do we need to switch on our load and initiate saturation? And we'll pick a load resistance of 5 kiloohms and an RB value of 2 kiloohms. And we'll assume that our supply voltage is 12 volts. Solving these equations that we had in the previous slides, we start with the load current IC, which is equal to the supply voltage minus the voltage drop from the collector to the emitter, divided by the load resistance, and that gives us 2.4 milliamps. Then we can use that relationship between the base current and the collector emitter current to obtain the base current of 0.024 milliamps, and that's quite a small current. Finally, we can solve for Vin using that relationship obtained from Kirchhoff's voltage law. And when we apply that, we find that Vin needs to be about 0.75 or so. So to switch on the load, we need an input voltage greater than 0.75. And that will place our BJT in saturation. And of course, we know that a microcontroller digital high signal can be either 3.3 volts or 5 volts, and so that will be more than sufficient for Vin in this case. Now, another thing we'll use BJT transistors for is to build something called an open collector output. And open collector outputs are used to connect certain types of sensors to digital I/O pins, digital input pins on the microcontroller. And what they'll allow us to do is take sensors with different output ranges, and we can then read them as either digital high or low at our desired logic voltage, which is either 3.3 volts for some microcontrollers or 5 volts for others. Here's an open collector output circuit shown at the bottom left of your slide. And you can see that the output of the sensor drives the base of the BJT. Another element that's important is RP. That's the pull-up resistor that connects the reference voltage V plus to the output voltage connected to our collector. And that V plus is our digital logic voltage, 3.3 volts or 5 volts. When our sensor's low, our BJT is when the sensor's digital low, so small enough to place the BJT in the off state, then no current's going to flow from the collector to the emitter, and thus V out is going to be 5 volts. There's no current flowing through that pull-up resistor. Now, when the sensor's high, that transistor then gets placed in saturation mode, and current flows from the collector to the emitter, and that's going to drop V out now down to ground. So you can see that V out is going to exist either at our high logic voltage or at our ground or logic low voltage. Looking at an example of where we might use an open collector output, we can talk about an encoder. An encoder is a sensor that connects to a rotating device to measure either its angular speed or angular position. Now, encoders output a square wave as that rotating shaft rotates. So it alternates between high and ground, and we can see what that square wave looks like at the bottom left. So that square wave indicates the rotation speed of the motor, the frequency of that square wave, and so oftentimes we want to read whether that signal is high or low with our microcontroller. So to be able to read that square wave, we might need to adjust the square wave positive voltage to a particular logic level, for instance 3.3 volts or 5 volts for a particular microcontroller. As a result, most encoders have an open collector output that allows you to adjust that output voltage easily. So you can attach that open collector output to a pull-up resistor, and as a result, your square wave will have the desired logic high value of 3.3 or 5 volts or something else. So here's the encoder mechanism as well as the open collector output that's usually attached to it. So the encoder will have a ground output, and it will also have an open collector output, and those are the two output wires that you can then interface to. And internally, the encoder output signal is then connected to the base of the BJT, and the collector and the emitter are connected to that open collector output and that ground respectively. What we'll do then when interfacing with a microcontroller is to connect the open collector output to a high reference voltage, 3.3 volts or 5 volts, through this pull-up resistor, and then we'll read the voltage drop between this reference voltage and the pull-up resistor as our output. And then we can read the ground directly. Now, if we read those two signals, the output and the ground, we read the voltage difference between them, that will give us our square wave. As a result, it's very easy to take an encoder and connect it to a microcontroller that uses 3.3 volts, and then take it again and connect it to something that uses 5 volts, and the only thing you have to change in that case is your reference voltage V high. Let's look at specifications for some common BJT transistors. You can see the maximum collector emitter voltages and the maximum base emitter voltages that these BJTs are designed for. But it's also important to look at two other specifications, which is the maximum collector current, IC, and power dissipation. It's important to identify an appropriate BJT for the application you're looking for that allows the appropriate amount of current to pass through. So for instance, for a particular motor, If you need to drive that motor with 1 amp of current, then you need to make sure that the maximum collector current through your BJT is greater than 1 amp. Furthermore, you have to make sure that your BJT can dissipate the appropriate amount of power for your application. Because so much current passes from the collector to the emitter when the BJT is in saturation and our load is operating, our BJT will dissipate power. So we need to make sure we have an appropriate power rating for our BJT, and we might also want to attach it to a heatsink. To summarize what we've learned in this lesson, BJT transistors are semiconductor elements, and they're used often in mechatronics for transistor switching circuits, where we have low power devices such as microcontrollers used to switch on high power loads such as motors or LEDs. We can write a series of equations to determine the needed input voltage to switch a transistor circuit on and off. Finally, open collector outputs are used commonly when interfacing sensors with microcontrollers that allow sensors to be converted to different logic levels and be read with microcontroller digital input pins.